Okay, so welcome to today's session where we are solving questions from chemistry tutorial sheets. Okay, so I urge you guys to be interactive. If you don't understand anything, just let me know. So I try to explain it to you. Okay, so we'll go straight into tutorial sheet, tutorial sheet 3. Okay, so the first question is the organic compounds are considered as compounds of carbon, and then they are saying explain why. Okay, so I believe all of us here know why organic compounds are considered compounds of carbon. Okay, so these organic compounds, they are considered as compounds of carbon, okay, because carbon is the main element that is present in all organic compounds. So if there's an absence of carbon in that compound, then we can't say that that compound is an organic compound, okay? So for it to be organic, then carbon must be present, okay? So you explain that it's because carbon is the main element of all the compounds, okay, that are called as organic compounds. So that's the reason there. So it's simple. Carbon is also known as the element of life, okay? So meaning all the things that we use, they involve carbon compounds, okay? They involve carbon compounds, and those carbon compounds are what we are calling as organic what? Compounds. So in everything that you use, there's organic compound there. So carbon is a very important what? Element. And organic chemistry, just the study of carbon, okay, and the compounds of carbon. So that's how we can explain this one here. Okay, and then number 2, this is number 1B, I mean, they're saying, is carbon a metal or is it a non-metal? And then they are saying explain. Okay, so I'm posing this question to you guys. Anyone who can try? Is carbon a metal or is it a non-metal? And then you also give us a reason why you are saying that. Hello? Is carbon a metal or a non-metal?
Maybe first to give it a try. I would say it's both a metal and a non-metal because of its position in the periodic table and its ability to combine with both the metal and non-metal.
Okay. All right, so that's good. Anyone else who can give it a try?
I think carbon is neither a metal or a non-metal because it can be whatever it wants to be at a given moment.
Come again.
It
I
can
didn't get what you said. You're saying?
I'm saying, you can get me now?
Yes, I can get you now.
I'm saying I think carbon is neither a metal or a non-metal because it can be held in both ways depending on what it will be reacting with. Sometimes it can be a metal or sometimes it can be a non-metal.
Okay, so yeah, so that's good. So there's that understanding, okay? So some people, they say it's neither a metal nor is it a non-metal because of its behaviors when reacting with different elements. So carbon is in group, is it group 4 there? So it's in group 4, if you consider the odd numbering of the groups. So carbon is in group 4. Then on its left, you have 3 groups of metals. And then on its right, you also have 3 groups of non-metals, excluding the group for the halogens, okay? So some debate that it's neither a metal nor a non-metal because of the reason that you've stated, okay, because of its behavior. But generally in the compounds, okay, we can classify carbon as a non-metal. Why? Because the principal bonds that it forms, okay, they are covalent bonds. And we know that covalent bonds are a characteristic of what? Non-metals. So in principle, some may say that carbon is a non-metal. Why? Because carbon forms covalent bonds by sharing electrons with other what? Elements. Okay, so you can also say carbon is a non-metal if you are on the debate of the non-metal side. So you can also say that carbon is a non-metal, okay, because it can behave as a poor conductor of electricity. Okay, so we know that those elements on the periodic table, if something is a metal, okay, then it will have the ability to conduct electricity. Okay, but if it's a non-metal, then it won't have the ability to conduct electricity, or it can conduct electricity at a very slow rate. Okay, so that shows that it's a what? A non-metal if you're using that debate. Okay, so and then we go to problem 2 here. They're saying carbon is known to combine with any other element on the periodic table, and no other element has been observed to do the same. Okay, so that's why carbon is unique. And then they're saying suggest the source. So the most important thing here is this word here. Suggest the source of carbon's ability to combine with any other element on the periodic table. Okay, so the source of carbon's ability to combine with any other element you can simply say it's due to the stable hybridized orbitals that are formed when carbon is in its excited form. Okay, so I hope you're able to understand this word hybridized. Okay, so when we are learning atomic structure, before we came to this organic chemistry topic, okay, in that atomic structure, we learned about the 4 quantum numbers, and we also learned that in an atom there are what we call as orbitals, right? So orbitals are just those specific locations where you can find specific electrons. So when you have an element, okay, it will have orbitals, and then when those orbitals they combine, okay, when one orbital combines with the other, they form what we call as hybridized orbitals. Okay, so what is the advantage of these hybridized orbitals? The advantage is that those hybridized orbitals will be more stable, and they will create a strong bond with other elements. Okay, so I think I should show this. Try to show it. Okay, so we know that we have these 2 orbitals. We have the s orbital, which looks like a circle, and then we also have a p orbital there, which looks like something like this. Okay, so if this s orbital is on its own, okay, it will be less stable, and then even the p, when it's on its own, it will be less stable. So what happens when carbon is excited? Okay, so by carbon is excited, we mean that some of the electrons in the carbon have gained energy and they want to move from one energy level to the other. Okay, so when that carbon is in that excited state, what happens to these orbitals here? Okay, they combine, okay, to form one orbital, and that one orbital is what we call as a hybridized orbital. So when that hybridized orbital is formed, it will have the ability to form bonds that are much stronger than if it was not what hybridized. So if we can show the hybridization of this and this, one of them can be I have this, and then I also have this. Okay, so these guys here will combine and form a stronger what? A stronger orbital. Okay, so and then this stronger orbital here will have the ability to combine with other orbitals from the other elements more strongly than any one of these would. Okay, so that's the source of carbon's ability, okay, to combine with any other element on the periodic table. It's because of the stable hybridized orbitals that it forms when it's in what? The excited state. Okay. So that's the reason there. And then, so question 3 now. Okay, so before I go to question 3, I would like to state 2 important properties of the carbon. So carbon is what we call as tetravalent. Okay, so tetravalent simply means that it forms 4 bonds. Okay, so how do you write this word? Tetravalent, like this. Okay, so this simply means that carbon forms a maximum of 4 bonds. Okay, so in all the organic structures that you're going to see, carbon will always be bonded, okay, 4 times. If carbon is not bonded 4 times, then it means your structure is wrong. Okay, the structure is very wrong. And then the other one is what we call as catenation. So this is a very important property, and this same catenation here will help us answer question 3. Okay, so what is catenation? Catenation is just the ability of carbon to bond to itself many times. So you can have a very long chain of these carbon to carbon bonds, okay, because of this property here. Okay, so carbon has this very 2 important properties. So take note of them. Okay, so when you see tetravalent, it simply means it forms 4 bonds, and its valence is also 4, right? And then when they say catenation, they simply mean the ability of this carbon to bond to itself many times. Okay, so you can have a chain of carbon atoms, like millions of them. For example, a very good example is in DNA. So in DNA there you find a very long chain of carbon atoms, billions and billions. So it's possible for carbon to do that because of what we call as catenation. Okay, and then let's answer question 3. So question 3, what does it say? So question 3 there, they're saying carbon compounds are very useful in the maintenance of life. For instance, in the reading of the number of parasites from the human body. State the major property. Okay, so this major property is what I'm from explaining. Okay, so state the major property of carbon compounds in which carbon plays the decisive role to fulfill its role in pharmacological medicine. Okay, so the reason why carbon plays a very decisive role in pharmacological medicine is because of one property. Okay, and that one property is what I was explaining, the catenation property. So you can say the major property of carbon that plays a decisive role in pharmacological effectiveness is what we call as catenation. Okay, so this is the ability of the carbon atoms to form long chains and complex structures by bonding with what? Other carbon atoms. So because of that property, okay, because of that property, the body is able to form complex compounds, and those complex compounds are very much important in the what? Pharmacological medicine or pharmacological aspects. Okay, so it helps in maybe you are sick, okay, and because of those carbon atoms that are very long, to form a complex molecule that will be able to help in alleviating that what? Sickness that you're feeling. So that property is what we call as the catenation property. So take note here, catenation like that. It's because carbon is able to bond to itself in very long chains like that. Okay, and then question 4, we're saying define the following terms as they are used in chemistry. So these are very simple. So the first one there, they're saying what? Yes.
Sorry. Is catenation the same as chirality? Because one time we revised the tutorial sheet in class, they told us about chirality.
Okay, chirality, no, it's not the same, but it's also an important property there that you can mention. Okay, so chirality just means the carbons are able to arrange themselves in different aspects or in different ways to form different things. Okay.
Okay.
Yes, so they are not necessarily the same with the catenations. Catenation just means they can be able to be joined together, like to form very long chains. And then the other one forms, they can form different arrangements, okay?
All right.
Okay. Okay, and then they're saying define the following terms as they are used in chemistry. So what is an ionic bond? Okay, so we know that an ionic bond is just simply, we can say a chemical bond formed as a result of donating and accepting what? Of an electron. So a good example of an ionic bond is what is formed in sodium what? Chloride. So sodium chloride here, this sodium atom, okay, will donate an electron. So it will lose an electron here. I think let me write it here. So if I have sodium here, and then there are this chlorine like this, okay? So this sodium here will donate a proton, not a proton, I mean, it will donate an electron to this chlorine here, okay? And because this one has lost an electron, it will become what? Sodium plus. And then this one, because it has gained an electron, it will become what? Chlorine minus. So you have charges there, okay? And because these charges are opposite, okay, they will attract together. So as a result of these charges that the sodium and the chlorine have here, okay, they will move closer together and they'll form a bond to form what we call as sodium chloride. So that's what an ionic bond is. It's just a chemical bond that involves the what? The donating and the accepting. So there should be one that is donating, which is the sodium in this case, and then the other one is receiving, which is the what? The chlorine. And because of the charges that they're going to attract together to form a what? A bond. So that's what an ionic bond is. And then a covalent bond. So in a covalent bond, there is no movement of covalent. Okay. So in a covalent bond, there's no movement of the electrons. The electrons are just shared. Okay. So the electrons are just shared. So a good example, we can say a hydrogen molecule. Okay, so this hydrogen molecule forms because of a covalent bond. So we know that if I draw the atom of the hydrogen here, it will just have one electron there, and then there it will have one proton. Okay, and then another hydrogen atom there will still have one proton, and then it will have what? One electron there. So these electrons here, or the atoms, the way they are, we know from the periodic table that all the atoms try to obtain a stable state of the electrons. Okay, so a stable state of the electrons can be 2, it can be 8, it can be 18. Okay, so these ones here, since they have one electron, okay, they will tend to be stable. And what will they do? They will come to grow. They'll come close together, and then they will share the electrons. So you have this electron from this guy, and then another electron from the other guy. So when they share these electrons, it means this first atom here, okay, will have 2 in its outermost state. Even this one here will have 2 in its outermost shell. So they will balance like that. Okay, so that's what a covalent bond is. It's just a bond, okay, formed by the sharing of what? Valence electrons. Okay, so specifically valence electrons, not any other electrons. So the electrons that should be shared there, only those electrons that are in the outermost shell. Those are the electrons that should be what? Should be shared. Okay, and then what is the other question here? We have question 5. They are saying using sketches, show the formation of the sigma and the pi bond. Okay, so in all the bonds that you see, okay, in all the bonds that you see, you have what we call as the sigma bond. Okay, and then in multiple bonds, like the double bond, a triple bond, you will see what we call as the pi bond. Okay, so these sigma bonds and the pi bonds, they result from the mixing of the orbitals. Okay, so remember I said we have the s orbital and the p orbital. Okay, so the sigma bond is formed when an s orbital joins another s orbital. They will form a sigma bond. Okay, and then you also have a sigma bond when you have an s orbital and the p orbital joining together. And then we also have a sigma bond, okay, when a p orbital and the p orbital overlap head-on. So meaning their heads overlap like that. And then the pi bond, it's only formed by one type of overlapping. And that overlapping is a p to p orbital sideways overlap. So here they're saying, using sketches, so the formation of the sigma and the pi bond. So for the sigma bond here, we are going to have 3 sketches. And then for the pi bond, we're just going to have what? 1. So here we're going to have 3, and then here we have 1. So let's do that now. So we know that the pi bond, the sigma bond, let me write it here, sigma, represented by this symbol like that, okay? It can be formed s and s orbital, then you can have s and p orbital, and then you can also have p and p orbital head-on. Okay. So how now do we sketch the formation of these? So you're going to draw one s orbital here. So this is the first way. You're going to say this is my s, and then plus another s orbital. Okay. So when these combine, they'll form a hybridized orbital like this. Okay. So the bond that will be formed here between this s and the s orbital, it will be called the what? A sigma bond. Okay, so this is one way we can form the sigma. And then another way, it is when we have an s orbital and then plus the p orbital. You know the p orbital is like this, right? So we have the p orbital there. And then these 2 orbitals, they combine or they overlap. Okay, so they will form a sigma bond as well. So you have your s, and then they overlap with the what? With the p. So you have your s here and the p. What you form here is still a what? A sigma bond. Okay, and then another way in which you can form a sigma bond is when you have 2 p orbitals that are overlapping what? Head-on, like this. So when these combine, you have something like this, something like this. So the bond that is formed here is also what? A sigma bond like this, even there. Okay, so you can form these sigma bonds in 3 different ways. So this is the first one, second one, fourth one. So take note of this. When we are talking about hybridization, they will be very important for us. Okay, and then how do you form the pi bond? Okay, so we said the pi bond can only be formed by one type of what? Overlapping. Okay, so you have a p orbital that will be represented in this way. Okay, and then plus another p orbital that will be represented in this way. So when you add these 2 here, okay, and they form a bond and sideways here, will form a what? A pi bond. So you can have something like this. Okay, that kind of bond. Okay, so let me draw it. Like this. So here the bond that will be formed, okay, because these p orbitals here, so this is the p orbital and then this is the p orbital. So these p orbitals have overlapped sideways. They are not head-on like we saw here, okay? So this is a sideways overlapping. So when the overlapping there is sideways, we get what we call as the pi bond. Okay, so this is how you can sketch the formation of a sigma and the pi bond. Okay, and then let's go to the other question, which is number 5b. Okay, okay, so here they're saying what kind of N-to-N bonds do you think is present in the nitrogen molecule? N subscript 2 there. Okay, so the first thing to note is that in the nitrogen molecule, we have a triple bond that is present there. Okay, so for us to find what type of bond is the end-to-end bond, we have to draw the Lewis structure of this guy here. Okay, and how do you draw the Lewis structure of this guy? We just say, here I have two atoms of nitrogen. Okay, so you get the total valence electrons for this and the total valence electrons for this, and then you add them. Okay, and then we know that in the nitrogen molecule, there's always a triple bond between these two N and M. Okay, and then you can distribute the other electrons on the other side. Okay, and then that will help you to determine what kind of bond this is. Okay, either it's a pi bond or it's a what? It's a sigma bond. Okay.
Sorry, so I come again. You said how can you identify to say this is the pi bond and this is the sigma bond? I didn't get that one.
Okay, I think I haven't mentioned yet. I was just saying that for you to get, for you to know that is it a sigma bond or is it a pi bond, you first have to draw the Lewis structure. Okay, and then from that Lewis structure, depending on the type of bond that you have, it's either a single bond or it's double bond or it's a triple bond. You can be able to tell what kind of bond it is. So I said the sigma bonds are present in any bond that you will see. Single bond, double bond, triple bond, whatever bond, a sigma bond will be there. But the pi bond, okay, is only present in multiple bonds. So for example, in the double bond, you will find a pi bond. In the triple bond, you find a pi bond, just like that. Okay, so now let's determine the bonds that are present in this nitrogen molecule here. So I'll go to my board here. Okay, I was saying, how do you determine if it's a triple, if it's a pi bond or it's a sigma bond? So we said in a single bond like this, indicated by a single line, you always find a what? A sigma bond. Okay, so in a single bond, you find sigma bond. Okay, and then in a double bond like this, one of these bonds will be a sigma, and then the other one will be a what? A pi bond. And then in a triple bond, if you have something like this, the first one there is always a sigma bond, and then the rest, they are pi bond. So you have one sigma bond here, and then you have two what? Pi bonds in a triple bond. Okay, so that's how you can determine. So there we were given a nitrogen molecule. Okay, so we are given a nitrogen molecule, which is this guy here. So he said, how do you determine this? We first have to draw its Lewis structure. So we know that the valence electron for nitrogen are what? Okay, so the valence electron for the nitrogen, the valence electron for the nitrogen is it 5? Okay, so 5 plus 5. So it means I will have 10 electrons to distribute. Okay, so I have 10 electrons to distribute. And then I know that if I put an N here and then another N here, if it's a nitrogen molecule, always guys, remember that in between the nitrogen and nitrogen, we have a triple bond like this. Okay, and then the other, so it means this one line here represents 2 electrons. This one line, 2 electrons, 2 electrons. So here I have 2 for 6 electrons. So we are remaining with what? 4 electrons. So you put 2 this side like this, and then you also put 2 on the other side like this. Okay, so we see that in this molecule we have a what? A triple bond. Okay, and what do we have in a triple bond? We have 1 sigma bond, and then we have 2 pi bonds. Okay, so in conclusion, you can say the nitrogen molecule has 1 N to N sigma bond. I don't know if this is the correct symbol that I've used. And then it has 2 N to N what? Pi bonds. Okay, so this is the conclusion that you should make there. Right, so if there are no questions, I'll move to the other question in this tutorial sheet 3. So, okay, so question 6 now, they are asking us about the geometry, okay, the geometric shape, okay, that would expect from our molecule to have. Okay, so for you to determine the geometric shape, the first thing, okay, you have to write the Lewis structure. Okay, so the Lewis structure, if you don't know how to write the Lewis structures, guys, there's a video on Drive. Please watch it. Okay, so because drawing the Lewis structure will help you in a lot of different ways. So for you to find what type of bond, for you to find the geometry of the molecule, of the geometry of the electrons, you always use a what? The Lewis structure. So for us to determine the geometric shape of this formaldehyde molecule here, okay, we have to draw the Lewis structure. And then from the Lewis structure, we'll be able to tell the shape. So I'll give you some things that you should memorize. Okay, So formaldehyde, okay, which is written as H2 and then double bonded to oxygen like that. Okay, so we have to draw the Lewis structure of this. So Lewis structure, we first add the valence electrons of these atoms that we have. So we have 2 from the hydrogen. We know that the valence electron for the hydrogen 1, and then plus how many valence electrons for the carbon? We have 4, plus how many valence electrons for this oxygen here? We have what? 6. And then when you add this, you get 12 electrons. So it means we have to distribute these 12 electrons into this molecule here. Okay, and the carbon there is always the central atom. Okay, so when you see carbon, it's mostly the central atom. So you're going to put your carbon here, okay, and then you're going to assign these electrons here. Okay, so you have one hydrogen this side, and then another hydrogen this side. Okay, and then you can put your oxygen on top here. So this hydrogen and this carbon, okay, they will share the 2 electrons like this. And then even this side, they'll share the 2 electrons like this. So from 12, I've removed 4 electrons. So how many am I remaining with? 8. So I have to assign this 8 to these atoms that I'm remaining with here. So the carbon and the oxygen, they'll share 2 electrons like this. Okay. And then even this carbon here, it will have another pair down there of electrons. So I have 2, 4, 6, 8, meaning I'm remaining with 4. So that's 4, you can put 2 of them this side, then the other 2 this side like this. So this is the Lewis structure of formaldehyde. Okay, and then how do you determine now the geometry from the Lewis structure? Okay, so you determine the geometry from the Lewis structure by identifying how many points is the central atom connected to. Okay, so by points, it can be a single bond, it can be a double bond, it can be a triple bond, or it can be a lone pair. So this one here, this is a single bond, because we said 2 electrons, you can represent them with a line like this. So if I can represent this molecule.
Can you repeat on how you can count the geometry? You said how you need to count how many points?
Okay, just a little. Okay, so for you to find the geometry, you have to find how many points are attached to the central atom. Okay, so in this case, the central atom is this carbon here. So how many points are attached to this central atom? Okay, so this is how we count. If we have a lone pair that is represented by 2 electrons like this is one item. We count it as one item. If it's a single bond, like a line like that, we count it as one item. If it's a double bond like this, we also count it as what? One item. If it's a triple bond like this, we also count it as one item. Okay, so it doesn't matter what is attaching to the carbon here. As long as it's attaching to this carbon, we count it as one. So here we're just going to count. We're going to count how many items are attached to this carbon here. Okay. Okay. So how many items are attached? So we're going to count this bond here. Okay, this bond here and that bond there, and then we have this is that the lone pair down there? Okay, so we can conclude that this part here, the down part here, is a lone pair, right? Because it's not bonded to anything. Okay, so let's count the number of electrons to make sure there are 12 here. So if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we see that there are 12 electrons in this molecule. And then this guy here, the carbon, is attached to how many items? So we can see 1, 2, 3, 4. So we can see that it's attached to 4. So if it's attached to 4 items then what will be the geometric shape? Okay, so there's a guide. Let me just look for it here. And then let me tell you.
So is
Yes.
carbon attached to 4 atoms or is attached to 3? Because the other 2 electrons will remain as lone pairs, isn't it?
Come again?
I'm saying is carbon attached to 4 atoms or it's only attached to 3 atoms, which are 2 hydrogens and 1 oxygen atom, and then the other 2 electrons will remain as lone pairs, isn't it?
Okay, I get your view. Okay, yeah. So I forgot to mention one thing. When you are getting the geometric shape, you don't consider the lone pair. Yeah, I think I should have. I didn't mention that. When you're getting the geometric shape, you don't consider the lone pair. Okay, and then when you're there's also what we call as the electron geometry. So if you are getting the electron geometry, it means you have to consider this lone pair here. But this one here, because we are getting the geometric shape, so there's electron geometry and the geometric shape. So the geometric shape, you don't consider the lone pair, this guy here. So you just count the number of atoms that are attached to this. So we have 1, 2, and then we have 3 there. So meaning our shape would be what? Would be trigonoplanar, right? What did you find? Okay, yeah. So because this central atom here is attached to what? To 3 atoms. We have 2 hydrogens here, and then we have 1 oxygen on top there. We are going to say the shape is what? The geometric shape, we are going to say it's trigonoplanar because we are only considering the atoms. But if the question was find the electron geometry, okay, then we are going to consider this lone pair. And this shape here will cease from trigonoplanar to become a tetrahedral because we are considering the electrons. Okay, but since this one here is geometric shape, then we can say that this shape here is a trigonoplanar. So now, how do you know? Okay, so if I have 3 items attached, we call this what? Trigonoplanar. And then if I should start from 2. If we have 2 with a lone pair present, we say it's V-shaped like water. Then if I have 3, it's a trigonoplanar. And then if I have 4, we say it's what? Tetrahedral. I don't know if you learned what 5 is. It will become trigonal bipyramidal. Okay, so if it's 5, we are going to have trigonal bipyramidal like this, bipyramidal. If you have 5 attached. Okay, and then it continues just like that. But the most important, I think, for you guys are these, the V-shaped or the bent. So this shape here is also called as the bent. And then we have the trigonoplanar. And then we also have the what? The tetrahedral there. So because this carbon here was attached to 3 atoms here, we can say that the shape of formaldehyde is just what? Trigonoplanar. Okay. So I don't know if there are any questions there. Okay, then let's move to the other question. Okay, and then they're saying, would you expect the molecular ammonium ion, which is given by this, to have the same geometric shape as the formaldehyde? And then they're saying, explain your reasoning to support your answer. Okay, so the answer there, we can say, no, we don't expect it to have the same shape because the ion of ammonia there will have a tetrahedral geometry, okay? Because the central atom, which is ammonia, will be attached to 4 different atoms. So if I write it here, where is it? So if I write the ammonium here, which is H4 plus, so simply meaning that it has gained a hydrogen here, okay? So if I write the structure for this, it will be N attached to 4 hydrogens like this. So we have hydrogen there, another hydrogen here, and another hydrogen. And then we indicate that this is as a positive charge like this. Okay? So this guy here, the central atom, which is the nitrogen, it is attached to 4 atoms like that. So it means each shape there will be tetrahedral. Okay, each shape there will be tetrahedral. So it won't have the same molecular shape or the same molecular geometry as the formaldehyde that we earlier found, which was trigonoplanar because it was attached to 3 different what? Atoms. Okay, so that's the answer there on B. I think we are done with tutorial sheet 3. And then let's look at some of the questions from tutorial 4 now. Okay, so